Okay, so we are going to actually start the world of trigonometry. We've learned a little about angle measure in the first two sections of Chapter 7 here, and now we're going to revisit trigonometry for a bit. You guys have done right triangle trig before. We are now going to extend our world of trigonometry to beyond right triangles, and here's how we're going to do it. Let's suppose I put an angle in standard position, vertex at the origin. We'll call one side of the angle the initial side, coincides with the x-axis, and my terminal side is spun either in the counterclockwise direction to give me positive measure, or in the clockwise direction to give me negative measure. And let's remember that we can measure our angle in either radians or degrees. Unimportant for the moment. What is important is we have an angle here. Let's suppose, furthermore, that I have a unit circle superimposed on my axis, so the radius of the circle here is 1. By definition, and definitions do need to be memorized. There's nothing to be proved, there's nothing difficult, I don't think, in understanding this definition, but it does have to be memorized. Henceforth, for at least the next couple years, you need to just know this. And here's the situation. I have my angle here, I'll call theta. We're going to define the sine of theta, that is, if I put an angle in standard position on the coordinate plane, the sine of theta, if I have a point on the unit circle that is on the terminal side of that angle, the sine of theta is going to be the y-coordinate of that point in the unit circle, and the cosine of the angle is going to be the x-coordinate. And that's it. That's the definition, our definition for sine and cosine. And you can see that as my angle changes, as it increases, let's say from 0 degrees or 0 radians, as it heads on up, and gets bigger, my coordinates are going to change. And how do they change? Well, let's visualize that for a bit. As my terminal side here spins, what's going to happen to that x-coordinate? Well, this point on the terminal side that coincides with the circle is going to head up the unit circle in this direction, and that x-coordinate is going to get smaller and smaller. If I have a 0 degree or 0 radian angle, the x-coordinate is 1. And as I head up toward pi over 2 or 90 degrees, that x-coordinate is going to head down toward 0. What happens is that angle keeps spinning around as I head from pi over 2 or 90 down toward 180. Well, that x-coordinate, as that angle spins, as my point on the unit circle on the terminal side spins around, that x-coordinate is going to decrease from 0 and head down to -1 at 180 or pi. So that, in a nutshell, is the definition for sine and cosine. And again, note, it doesn't matter what measurement I'm in, either degrees or radians. Whatever I measure the angle in, I'm going to have some coordinates on that unit circle, x and y, and those are going to be my sine and cosine values. So you might wonder, coming up next, what happens if we're not on the unit circle? What happens if we're on some general random circle? How does our definition get modified here? Let's check it out. So, let's suppose we now want to consider a different circle other than the unit circle. So let's start off, I'm looking at my diagram up here. I've got my unit circle, radius of 1, point on that unit circle that coincides with the terminal side of an angle theta, labeled xy. Let's draw some other random circle in. It could be larger or smaller. We'll go larger for now, just to illustrate here. Larger circle. Let's let the radius of that larger circle be r, and let's label the points where the terminal side of the angle coincides with the larger circle as x1, y1. I then want to hone in on this part of the diagram, but I also want to drop down altitudes to the x-axis from my 2 points that coincide with the circle. And when I do that, I get this diagram over here. So I've just honed in, if you will, on this part of my diagram right here, creating two right triangles when I drop those altitudes down, perpendiculars down to the x-axis. So that's what I have then right here. So let's consider that, go back to geometry class for a bit, and what do we remember? We remember that if we have a large right triangle and a smaller right triangle in this type of diagram, the smaller triangle is similar to the larger triangle. They share an angle, they each have a right angle, which means this small triangle is similar to this large right triangle. What's that mean? Well, that means the ratio of corresponding sides are proportional. So that would mean, for example, in the little triangle here, x to 1 is going to equal x1 to r, or y to 1 equals y1 to r. And when we write that down, the ratios of corresponding sides of similar triangles are proportional. Let's note x over 1 is going to equal x1 over r, and y over 1 equals y1 over r. Well, x over 1 is x, and y1 over r is, or sorry, y over 1 is y. So let's take a look at that right here and consider back on our original diagram. We know the sine of theta is y, which is y over 1, and we know the cosine of theta is x, which is x over 1, and that means that by the definition I just gave you, my sine and cosine, the sine of theta is y, so that's going to equal y1 over r, and my cosine of theta is x, and that means it's also going to equal x1 over r. And if we consider our diagram here, again, let's blow our diagram up here a bit. Let's make it back a little bigger. Go in. That means that basically what I've shown then is my sine of theta equals also, in addition to y, it's going to be y1 over r, and the cosine of theta is going to be x1 over r. And that should be consistent. If you think about it with our original definition, what we're saying is the sine of the angle theta is the y-coordinate over the radius of the circle, and that's consistent with if we have a special case, specific unit circle, I'm going to have my sine is going to be equal to the y-coordinate over the radius of the circle. Sorry about that phone, but here we go. Let's summarize then. So if we have an angle in standard position, initial side, terminal side, spun, angle theta. We then have a more general definition that I gave you 2 slides ago. It's that the sine of theta is going to be y over r, and the cosine of theta is going to be x over r, and the unit circle is a special case where the radius equals 1. So again, that's our general definition. This diagram needs to be kind of ingrained. You should see this picture whenever you're asked for the sine of an angle. You should be imagining, well, it's going to be a y-coordinate, which is going to be a vertical length divided by a positive number, because the radius of a circle is always going to be a positive number. And the cosine of an angle, well, I'm looking for the x-coordinate of the point on the terminal side of the angle that coincides with some circle. It's going to be that x-coordinate divided by a positive number r. So that's, again, a visualization of what sine and cosine are. Again, sines and cosines are simply ratios. They're ratios of x and y coordinates over a radius of a circle that's superimposed on an angle in standard position. And that's it. Okay, geometry is also going to come into play here as we play around with sines and cosines. And you're going to want to remember, it'll be useful and save you some arithmetic if you can remember Pythagorean triples from geometry. And Pythagorean triples were simply nice round whole integers here, such that smallest squared plus middle squared equals large squared. And these were 5 of the ones that cropped up a lot in geometry a bit ago. How can that crop up here for trig? Well, consider the following. Suppose I've got an angle in quadrant 2, and its cosine is negative 15/17, and we're asked to find the sine of that angle. So first of all, again, you want to get a visualization. You want to figure out what does this angle look like in standard position? So if I know I'm in quadrant 2, the angle, the terminal side is going to spin around and be somewhere over here. Here's my theta, and I've spun that way. Now, could I have gone another way? Could I have spun around this way to get to the angle in whose terminal side is in quadrant 2? Sure. Could I have spun around multiple times to get an angle whose terminal side is in quadrant 2? And by saying that the angle is a quadrant 2 angle, it means to say that its terminal side is in quadrant 2. So I've got that angle there. I'm told the cosine is negative 15/17. One thing we remember is we have our definition of sines and cosines, and that entails that if I have a circle here in center at 0, 0, that the terminal side of the angle coincides with the circle at a point x, comma, y. And we know that the sine and cosine of that angle can be related to the x and y coordinate and the radius of the circle. So in this case, we're told the cosine of the angle is negative 15/17. Well, how can we visualize where that x and y are? Well, we could also drop down an altitude here, a perpendicular to the x-axis. This is our x, and this is our y. So I got negative 15/17. Could I simply label x to be negative 15 and r to be 17? And would I have then the cosine of my angle to be negative 15/17? Indeed I can, and that's what I'm going to want to do. If that's true, negative 15/17 here, I've got a right triangle and I'm looking to find that y. So Pythagorean theorem, 15 squared plus y squared equals 17 squared. If I know my special right triangles, I can simply say, you know what? Y is going to be 8. So then I can simply say that sine of theta equals 8 over 17, and I could say 8, 15, 17 right triangle to justify how I got that answer of 8/17 in conjunction with the diagram that I've drawn.